Okay, so let's talk about Albert Einstein and relativity. Back in the early 1900s, we were faced with this conundrum, and that conundrum was that the prevailing theory of electricity and magnetism told us that the speed of light should be constant in a vacuum. If you recall, the speed of light is c. That's equal to 3 times 10 to the 8 meters per second. Okay, this was a speed that was measured, and we were studying electricity and magnetism, building generators, and trying to understand how magnetism and electricity work together. And the theory that emerged indicated that the speed of light was always this value for everybody. Now, the problem with that is that you're all accustomed to this idea that if you're moving with respect to something, that your speed changes if the thing you're moving with respect to also has a velocity. So for example, if I had a car, here's my little car right here, moving at 60 miles an hour, mph, and I had somebody standing on the side of the road here, that car is moving 60 miles per hour relative to that person. But if this person is walking at, say, 3 miles per hour, then the relative speed of this car relative to this person now appears to be going a little bit faster, because we add these two velocities together, they're going faster, they add together, so the velocity that we would see from respect to the person now walking would be 63 miles per hour. If we were walking this way, right, the velocities would subtract, and it would appear that the car was only going 57 miles per hour. Right? And you're accustomed to this. This happens all the time. However, with the speed of light was 3 times 10 to the 8 meters per second for everybody. So that meant if I had a flashlight over here, here's a little flashlight with light waves coming out of it. If I was walking towards the flashlight, I was supposed to see the speed of light was c. If I was walking away from the flashlight, I was supposed to see the speed of light was c, and there was not any of this additive properties to it. This came out of the theory of electricity and magnetism. And of course, people thought, well, that's nuts. There has to be some additive properties because that's the way velocities work. So maybe the speed of light isn't really c with respect to everybody. Maybe the speed of light is c with respect to some background somewhere in the universe. And if we could only just measure that, we would know that that the speed of light was c relative to that background. And they had a name for that background. They called it the ether. And it was this mysterious background material, the ether, with which if you measured the speed of light with respect to it, you would always get c, but if you measured it in any other way, you would get a different value. And they measured it by a clever experiment where they took the Earth going around the sun. So here's the Earth going around the sun. And they figured if the Earth was moving relative to this ether, right? So here's this material out here we call the ether. We don't know what it is, but it's out there and it's the reference frame of the universe. If the Earth was moving relative to the ether in this direction and a ray of light came through, moving at c in that direction, then we should measure the speed of light on Earth to be whatever the velocity of the Earth was plus the speed of light, because that's what we have if that's the thing we're accustomed to in our everyday life. And if we were over here moving with some velocity in this direction, if this was the Earth here, and some beam of light came in with c, then we should measure c minus v over here, because we're moving with the light, so the light would appear to be traveling slower. And if we were over here traveling this way, we would just measure c because it's perpendicular, and over here we would measure c, it'd be perpendicular, and we would see no change in those two positions. And so the prediction was that if we were to measure the speed of light on the Earth, so we'll just call that c Earth, as a function of time, that it would oscillate around the value of c, that we know it to be with respect to the ether. And up here would be c plus v, and down here would be c minus v, and there you have it. So they decided to do this experiment. They developed an instrument that could very sensitively measure the speed of light. It was about 11 meters across. They put it in a laboratory, and they waited all year to watch this experiment take place. When they first started taking data, they had a data point here for the speed of light, and they had a data point here for the speed of light, and they had a data point here for the speed of light, and then they had the data point here for the speed of light and here for the speed of light. And as they kept doing the experiment, they did not measure any variation beyond experimental errors in the speed of light. So in other words, they got that the speed of light was equal to c as measured on Earth, regardless of what direction we were going with respect to it. So this was a challenge, right? So we didn't know what to make of that because it didn't make any sense with our everyday surroundings. And this was a paradox at the time, and they wrote these two things down. They said, okay, well, look, it's got to be that, physics, we all have to agree on the rules of physics. So the rules of physics have to be true for everybody, right? So the rules of physics have to be good in all cases. And then we had this experimental result that said that the speed of light was constant. And that was a measurement, right? So this is the thing that we figured philosophically had to be true, because otherwise we can't agree on anything. And this was experimentally true. But the problem is that if the speed of light was constant for everybody, then velocities don't add, and that goes against the way we think our physics works. And to give you an example of this, imagine you're a person right here, and you're walking along at 3 miles per hour, right? And you're throwing a ball up in the air. So you take a ball, you throw it in the air. Whoosh. Now, if you do this experiment, walking 3 miles an hour, you throw the ball up in the air, it drops back down, right back into your hand. You can juggle and walk at the same time, no big deal. However, if I'm watching you from the side, walking by, you're going this way, you throw the ball up, and it looks to me like it goes like this, because you've walked a little distance. You're still holding the ball, right? You threw it up in the air, you caught it, but I watched it go in an arc as you walked past me, right? So we have to agree on the outcome. You caught the ball. But from my perspective, the ball is moving at 3 miles per hour. And from your perspective, the ball isn't moving at all because you're carrying it. And so this is our velocities adding. That does not apply to the speed of light. This is the physics that they knew at the time. What can we do? Right? So people were very confused by this, and they tried to argue that the speed of light was incorrect. We have to make some more measurements, all these things to try and rectify this. But it took Einstein to come along to really do the brilliant thing. And the brilliant thing he did was he said, okay, look, this isn't a paradox. Let's just pretend, for the sake of argument, let's hold this idea in our head for just a second, that both of these things are true, that the rules of physics have to apply for everybody, and the speed of light is always constant for every observer. And let's see if we can make sense of what the implications of this are by just assuming that these two things are true. And so these became the postulates of what he called special relativity. And it was special because it only works in situations where the velocity is constant. So you have to be moving at a constant velocity. V is constant, no accelerations. And this was just his first stab at this. So we'll talk about accelerations a little bit later. So this was special relativity. The rules of physics are good in all cases. The speed of light is constant for everybody. And he said, let's just assume that's true because that seems to be what nature is telling us, and let's see what happens. And to do this, I want to work on an activity with you that we have here. We've got an activity in your workbook. So if you want to take a moment to pull up your workbook activity called Special Relativity, that is going to illustrate what happens if we hold these two postulates at the same time, and just for the sake of argument, pretend they're both true and see what happens. So we're going to do this using the state-of-the-art equipment of Einstein's day. And I want you to cast your mind back for a second and think about what this must have been like. So this is 1905. Einstein is living in a time where continents are being covered by trains. People have developed this awesome new device called a stopwatch that you can hold in your hand that tells time very, very accurately. I know that seems kind of crazy to think about that, but in 1905 this was a big deal, right? That you could carry time with you. People were starting to tell time by watches instead of the sky. They were starting to measure things precisely, and this was an era of high technology. And imagine, it doesn't seem like a high technology to us now, but imagine, if you've only ever gotten around by walking or by a cart, and then suddenly you can hop on a train and go 30 miles an hour, that's pretty impressive. So he used, in his little thought experiment, the most sophisticated equipment he could imagine, which was a train and a stopwatch. And here's the situation that we have. Here is a person sitting in a train, and they have the ability to measure, they turn on a light, and they can measure the time it takes for the light beam to travel from the light to the ground. Okay, and he called this a light clock. It was basically the ability for to count a photon or a bit of light going up and down and up and down. And he can time, using the newfangled stopwatch, can time the amount of time it takes to go from the top to the bottom of the train if I turn on the light. Okay, so he's going to use this as a clock, measuring the speed as we go. Now we're going to do this from two perspectives. We're going to do it from the observer's perspective inside the train, and the observer's perspective if you were outside the train watching it go by. The first situation is inside the train. If you are in a train and there's no windows, you can't tell if you're moving because you're at a constant velocity. So we're going to make this calculation. So we'll go and say that we time how long it takes to go from here to here, using the fact that we know that distance is equal to the speed, which we think is c at this time, because we're going to assume that c is constant, times time. Okay, so the distance is equal to rate times time. You use this equation all the time whenever you drive anywhere. If I take the rate at which something is moving and the time it takes, then I can measure the distance. In this case, we know what the distance is. The distance is the height of the train car, and I think I gave that to you. Yeah, 4 meters high. Okay, so the train is 4 meters high. So let's calculate how long it takes for the light to go from the top to the bottom. So the time is going to be the distance divided by the speed of light. Now in this case, the distance is 4 meters. The speed of light is 3 times 10 to the 8th meters per second. And so that means that the time is going to be 4/3 times 10 to the minus 8 seconds. Okay, seconds, very, very short time. Okay, but that's the time that it takes if the light is going at the speed of light, which is one of our postulates. Okay. All right, so that's the speed for that. So you can write that down in the first question to see how long it takes to do that. Then let's go to the second situation. The second situation is observing this from outside the train. So outside the train, I'm watching the train go by. This is just like you walking and throwing the ball. We have to agree on the physics, right? We have to agree that the light went from the top of the train car to the bottom of the train car. But in this case, the car, from my perspective, has moved 3 meters over. Okay, so we can draw this picture down here. If I look at this, the light starts here, and we have to agree that it hits point B, because it hit point B for the first observer, so it has to hit point B for the second observer. And from my perspective, the car has moved 3 meters. Okay, so the car has moved 3 meters. The light has still dropped 4 meters. And that's a perpendicular triangle right there. So if you recall from your geometry classes, the distance traveled for a 3, 4, 5 triangle is 5 meters. You can also find that from Pythagorean's theorem. That's 3 squared plus 4 squared is equal to 5 squared. But this distance right here is 5 meters. So the time it took is going to be, again, using that same equation, the time it took is going to be the distance divided by the speed. In this case, though, the distance is now 5 meters. The speed's the same because that's one of our postulates. 3 times 10 to the 8th, which means that the time, from my perspective, outside the train is 5/3 times 10 to the minus 8. Right? That's interesting because the person inside the train measured 4/3 times 10 to the minus 8. The person outside measured 5/3 times 10 to the minus 8. And all we assumed was that we have to agree on the outcome, which is that the light goes from A to B, and that the speed of light is constant for all observers. And what changes is the amount of time we calculate for the event to occur. And at this point, Einstein sits back and says, whoa, wait a second. So what this means is that when these two people get together to talk about what happened, the person on the inside thinks 4/3 times 10 to the minus 8 seconds has elapsed. The person on the outside thinks 5/3 times 10 to the minus 8 seconds have elapsed. They have a different answer, right? In other words, less time has passed for the person who is moving. And they say, what? That doesn't make any sense. But Einstein said, look, this is the way it works if we assume these two things are correct. Now at the time, so there's a name for this effect, and it's called time dilation. And time dilation says that the moving person, so the person who's moving, experiences less time. Another way to say that is that moving clocks appear slow. And you can think about that like the person on the inside has a clock and it went 4/3. The person on the outside has a clock and it went 5/3. So when they compare their clocks, the moving clock appears to be slow, and you'd have to advance it forward to have it be the correct time for the person on the outside. Now, the reason this isn't a big effect, we're talking about nanoseconds here. This train is still moving extraordinarily fast even to see nanoseconds. So the reason you don't notice this when you're, say, driving to Salt Lake is because you're going really way too slow for this effect to be seen. And but Einstein said, look, it must be happening all the time. We just don't notice it when we're moving really, really slowly. But of course, people were freaking out about this because it was saying that this immutable property of time, this thing that we're measuring with a watch, which just tick tock goes on, somehow is different depending on how you're moving through space and time. And all Einstein could do is throw up his hands and say, well, let's see if we can find some experimental verification for this. And the experimental verification for this has been done. We've taken clocks and flown them in orbit and compared them to clocks back on the Earth, and this occurs, that moving clocks experience less time. And this is not to say that somehow the clock is affected or somehow the perception of time is affected. It's just that the moving person experiences less time. So if you were to move at some great speed for a little while, your time is slower, and so you would experience less time. Your heartbeat would slow down. You wouldn't notice anything, right? Because it would just be you walking around, but instead of a week passing, an hour would have passed. So let's look at the implications of this for space travel, because this is exciting, right? Space travel is where this gets to be something that's very, very useful. So your activity this time includes these calculations, which you can do and answer the questions. And then the second activity I wanted you to do is seeing how time dilation affects spacecraft travel when you're going really fast. So in order to do this experiment, we have to recall our Doppler effect. We emits light like this from this point. We move a little bit, it emits light like this from this point. It moves a little bit, emits light like this from this point. And we recall that the waves get stretched out behind and get compressed in front. Okay, so that happens. We have blue shift and red shift. This is the red shift. This is the blue shift. And that happens for anything that's moving. Well, if you have a beacon, it does the same thing. If I shine a beacon and make it blink, say every 6 seconds or something like that, in front of the moving craft, you'll see it happen closer together. Behind the moving craft, you'll see them happen further apart. Okay, so we're going to use this property of Doppler effect to illustrate how time dilation works for space travel. So the situation we have here is we have a person who's flying in a spacecraft, and they're sending flashes out from the spacecraft, and from the spacecraft's perspective, every 6 minutes, it leaves the spacecraft. Okay, but because when it's traveling away from the Earth, the time dilation or the Doppler shift causes the intervals to stretch out, that means it's received on the Earth at 12-minute intervals on the trip out, and it's received on Earth at 3-minute intervals on the way back. Okay, so this is a ship that's traveling so fast that it can have these intervals compressed and expanded as it's going. So let's see what happens when we do this, right? And you can follow along. What we're going to do here is we're going to keep track of the time on the ship. Every 6 minutes, this thing flashes. On the way out, every 12 minutes, we see one on the Earth. And on the way back, every 3 minutes, we see one on the Earth. And we'll see how much time has elapsed in both cases. Okay, so we start this one. We'll do the flashes sent on the ship first. This goes from 12 to 12:06. The next one is 12:12. Right? The next one is 12:18 and 1 o'clock. Okay, so that's just keeping time on the ship. We're just looking at the clock every 6 minutes. But because we're moving away from the Earth, we get this dilated time expanding out. The flashes going away from the Earth. So here we get 12:12. Okay, this is what we see the flashes on the Earth. So we see a time difference. We're already measuring a different time. 6 minutes have elapsed. 12 minutes have elapsed. This is going to be 12:24, 2 o'clock. Okay. So we're seeing a time difference here. This is going out, measured on Earth. Only a little bit of time has passed on the ship. More time has passed on Earth. But now the ship has to come back. It lands, turns around, comes back. When it comes back, every 3 minutes elapses. And you can see that, again, we just add 6 on the ship. Nothing changes on the ship as far as you're concerned. This is 106, 112, etc. But only 3 minutes is elapsing as seen on Earth. So this is 2. We start at 2 o'clock. So this is 2:03, 2:06, etc. And as you go down here, you're going to find that there's a time difference between these two. So you can finish that one. And you'll see that, as it stated in the beginning, that there's a time difference of 2 hours for the journey versus 2.5 hours for the person back on Earth. So this is the twin paradox, that if you're traveling fast enough, you can have somebody fly out to a distant star, come back, and they'll be younger than the person they left behind. This is exciting for space travel and time travel, because as you get arbitrarily closer and closer and closer to the speed of light, this effect becomes greater and greater and greater. And as it gets bigger and bigger and bigger, the time differences get bigger and bigger and bigger, so that if I were to send you to Alpha Centauri at 99.99999% the speed of light, you would go away, come back. I would be 8 years older. You would have only had to pack a lunch. So it's a pretty impressive little experience, this special relativity. Now, again, sounds nuts, and people thought Einstein was a little off his rocker when he first wrote this stuff up. He was winning Nobel Prizes, but not for this. He was winning Nobel Prizes for other work. At the time, it was not sure if this had been would be borne out. And part of the problem at 1905 is that he hadn't included anything about acceleration. So let's go ahead and come back to our relativity here and just write down the 2 postulates of relativity. And I'm going to abbreviate these things. I'm going to say the first one is that physics rules. We have to agree on the outcome. Right? Physics rules. Just say physics rules. And 2, c is constant. Now the implication of this is time dilation, which is a little bit hard to swallow, but if you agree that we have to agree on the results, and you agree that the speed of light is constant for all observers, then we have to accept that time is different. Now, if you think about time dilation for a second, it's not so strange if you think about it, because you're used to relative space. You know, if I imagine an xy position, so here's x and here's y, and I have you standing at the origin 0, 0, and I'm standing over here at, say, 0x and y1, then I measure a distance here, which depends on where I'm standing. If I move over here, the distance is a little bit different. If I measure from up here, even though I'm in the same spot, the distance is different. So everything's relative. You have no problem with that. All Einstein is saying is that you remove from the axis one of a position and put time instead. Right? And we never notice this because you and I are always experiencing the same time, because we're moving together on this planet at the same speed. And so if I measure the time coordinate, if I were to give you my coordinates in x, y, z, and time, I have a position x, y, z, and we have a time, and the time difference between you and me is 0. Now the difference in the twin paradox is that after you've traveled at near the speed of light, now the difference in time is not 0. So there's it's another coordinate, but we never notice that it's different because we're always moving together on the same planet. So Einstein had these two things together. The only problem is it only worked for constant velocity. This was special relativity. Remember, special relativity only dealt with v equals constant. So in order to deal with accelerations, which is a changing velocity, we have to come up with something else. And so his idea was, well, wait a second, how can I make accelerations part of this? And his deal was you couldn't be able to tell the difference. Everything had to be relative. So I couldn't tell the difference, for example, between a person standing on the planet Earth, being accelerated down at g equals 9.8 meters per second squared, which is how strong the Earth's gravity is. I couldn't tell the difference between that situation or a person in a spacecraft, forgive my art here, a person in a spacecraft that is being accelerated up with g. right? And the reason is because if I have a spacecraft accelerating up, then I'm just floating in space. The spaceship pushes me up, so if it's pushing me up, I'm going to feel a force pushing down with g. So this spacecraft pushing me up, I feel like I'm going down, and I couldn't tell the difference between these two experiments. This is called the principle of equivalence, or the equivalence principle. And the thing that's equivalent here is that there is no difference between the mass that's being moved by the inertial force over here, this is an inertial force, or the mass that's being affected over here, which is a gravitational force. In other words, these two masses, inertial mass, which is the property that you measure when you push something, and the gravitational mass, which is the property you measure when you pull on something with gravity, were the same. And people hadn't thought really hard about it until Einstein, but Einstein was the first person to say they don't have to be the same, but they are. Right? There's nothing in the universe that tells us they are the same except for special and general relativity. Right? So Einstein was the person who came up with an explanation for why these things have to be the same, and no experiment could be done that could tell the difference between these things. And this is where it brought up the way to test these ideas of relativity beyond a shadow of a doubt. And that is, imagine an experiment. Remember, Einstein says no experiment can tell the difference between these two situations. So an experiment is this. You're in the spaceship and you happen to have a laser beam and you shine the laser beam on the wall. Right? Shine the laser beam on the wall. You're in a moving spacecraft. Remember, if I throw something across a spacecraft and the spacecraft accelerates away from it, then that means that it's going to hit on the wall lower than where I shot it from. So in the spacecraft, the light beam is going to appear to bend. So I'll shoot it from here, but it'll land down here. So in this moving spacecraft, just by the properties of its accelerated motion, you'll notice the light ray didn't move. The spacecraft did. Okay, but Einstein said you can't tell the difference between these two things. So that means if I shine a laser beam on the Earth, right, it should bend by the same amount. This little distance right here. It should have, I would expect it to go like this, but it bent. And this is what Einstein's saying in relativity. This is a prediction. He's saying that gravity should bend light, even though it has no mass, simply because of the principle of equivalence. And everyone said, well, that's crazy, but I can imagine an experiment to test this, right? I can imagine an experiment to test this. And that experiment is this. We go outside and we look at a star field at night. So here's a star field at night. Right? We make a map. This is what the stars look like. Then we wait until just the right moment when the sun, now this is daytime, right? Because the sun's out. The sun passes in front of that star field at the very same time that it is eclipsed by the moon, so that the sun's light is blocked out so I can see the stars in the daytime. Now, if Einstein's correct, the position of those stars should appear to change because the light is being bent by the gravity of the sun. So if we have a star here, there's a different picture here, we have a star here and we have the sun here, and you're observing it here on the Earth, the light should bend around the sun, and that will make it appear like the light came from over here. So the position of the star will shift a little bit. Well, Einstein predicted this. He suggested a way to test it. They had to wait several years to do it. They sent people all over the world to observe this eclipse, and sure enough, as soon as the sun passed in front of the stars, their positions had changed, and light was bent by gravity. So Einstein was correct. He was borne out in every experiment we've ever done. The following three postulates of general relativity, they include the fact that physics is the same for everybody, physics rules. They include the fact that c is constant. And finally, they include the fact that inertial mass is the same as gravity mass. And that's the principle of equivalence. This is general relativity, sometimes abbreviated GR, and it rules the universe. It's been documented in every experiment that we've ever done. In addition to that, it implies that time travel, at least in the forward direction, is possible because we have time dilation. I can send you on a spacecraft at very close to the speed of light, and you can come back 1,000 years later from my perspective on the Earth, but you haven't aged at all. The second thing is it introduced a concept called spacetime. And spacetime is the last thing we want to talk about today, because this is the thing which you are currently sitting in, this space-time that surrounds you, and it's something that you are immersed in all the time, and we never even really think about it. So we want to talk a little bit about how we explore space-time and measure space-time. So let's take a look at what we mean by space-time. This was invented effectively by Einstein to explain general relativity, and the fact that space-time exists is space-time is the stuff that tells things how to move, right? It's if I put down space-time, things move through it. If I bend or warp space-time, that changes the trajectory of anything that's moving through it. And Einstein connected space-time, the thing that dictates how things move through space, with mass. Mass bends the space-time. Space-time tells stuff how to move. Okay, and space-time is a four-dimensional construction where we have position, x, y, z, and we have time, and they are all equivalent relative dimensions. So this is a big concept. I can feel your brain starting to explode. So let's do some little experiments to see if we can get a handle on how space-time works. Okay, we're going to think about this in 2 dimensions first because it's a little bit easier to visualize. So imagine a giant rubber sheet that's stretched across some kind of membrane, and it's flat. Now if I add weights of different masses on there, it's going to bend different amounts. So if I add a 1 kilogram or a 0.1 kilogram or a 10 kilogram, it's going to bend these things a little bit. Now, if I take an object now and roll it like a little marble, if I roll a little marble across one of the flat spots, it just goes straight, right? Because there's nothing to tell it to do anything different. However, when it comes by one of the masses that's deflecting or curving the space, it's going to curve whoop, whoop, like that, because it's like on a bank turn, right? It's just going to turn around that mass. Now you'll notice, as far as the trajectory of the object is concerned, it's going in a straight line, right? It's still straight on this curved space. And if I go around something that's less massive, the curvature is less, and so I get deflected less. If I go about something a little bit more massive, I get deflected a little bit more. Something really massive, I get deflected a lot. And it's this curvature which is dictating the motion of these objects. Now, for you to experience that, I want you to just kind of sit in your chair for a moment and think about the gravity that's holding you to the chair. That gravity that's holding you to the chair, you are a point object that is traveling towards the Earth that is currently being interrupted by the chair and causing you to stop. If I were to remove the chair, you would continue to fall. And you would continue to fall because you are falling down this slope of space-time. It's just you happen to be resting on a planet right there. And so Einstein's space-time explains gravity. Gravity is the curvature of space-time. This mass has curved space-time, and you are falling down that curve and just happen at the moment to be resting on the surface of the planet. Okay, so you're in space-time right now. You can feel it. Right? The cool thing about Einstein's space-time theory is that it gives gravity meaning. You remember Newton came up with gravity, and he had no idea what it was. He said, I don't know what this is, but it works. Einstein is coming along and saying, I know what gravity is. Gravity is the curvature of space-time, and the curvature of space-time is caused by the massive object. So this is the first connection between with gravity with a real thing, a real physical property of the universe. So again, just to illustrate this, if we go out from the orbits of the planets, this explains Kepler's laws. It explains all of Newton's laws. It gives us all of the motions of the planets. You can derive all of Kepler and Newton from Einstein. So they weren't wrong, they were just incomplete because they didn't understand what they were really looking at. And so here we have the orbits going around the sun, and if we have the Earth and Mars in circular orbits, they're following a closed curve on this that's relatively constant because they just go around their curve. Same with Mars here, but the comet comes in on an eccentric orbit and it speeds up as it gets closer because the curvature is greater here than it is out here. So it explains Kepler's second law, and it gives us everything that we had before. It also gives us gravitational lensing, which we talked about. This is going to become very important later. We use gravitational lensing all the time to detect things we can't see. And again, we'll talk about that when we talk about the structure of the universe. But this is the property that's been measured to confirm Einstein's general relativity. Now, we've got relativity, we can talk about black holes. Okay, so the last thing we talked about in stellar evolution was the evolution of high-mass stars, and we had a giant supernova explosion, and if the star was massive enough, it would collapse to form either a neutron star, or if it was massive, really massive, a black hole. But what is a black hole? A black hole, we said, was an object that once it collapsed, light could no longer escape. That the escape speed of a black hole was greater than the speed of light. But now we have a meaning for what this really is, this black hole. Whoops. Yeah, the black hole is basically you're taking a ton of mass and making it really, really small so that the curvature is nearly infinite. And so at some point along this, you get to something called the event horizon, where the escape speed is equal to the speed of light. So we can ask ourselves, what happens when we fall into a black hole? Well, if I have an object here and I start to fall gently towards a black hole in this direction, my speed will increase until I reach here and it's the speed of light. Now, I could orbit a black hole just fine, right? If I was in a circular orbit around a black hole, you wouldn't even notice. I mean, there wouldn't be any light, but you could orbit this thing indefinitely and you would never get sucked into the black hole. But if I decided to throw you into the black hole, then you would go all the way down to the event horizon. But you're reaching the speed of light, so time dilation takes hold. So here's the question: what would it look like to experience falling into a black hole? Well, let's imagine that we do this experiment. Let's have two people out here. Let's put a spaceship out here. I'll just make it a little box spaceship out here with a person in it. And we take another person, put them in a spacesuit. Now, the spacesuit has to be pretty special because the tidal forces of a black hole will rip you to shreds, but we put you in a spacesuit that will protect you. We make it a little bubble, right? And on the top of the bubble, we put a beacon that is blinking, say, every second. It just goes blink, 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 like that. So I toss you into the black hole. From your perspective, if you're going to the black hole, I toss you into the black hole. From your perspective, you just go falling in. Whoa, this is so cool. Because you don't notice any different. You just go, wow, look, it's a black hole. This is exciting. What's in here? Let's go check it out. Now, from the outside, though, they're watching your light to see the progress. So you're blinking, and it goes blink, blink every second, but now we get time dilation as you approach the speed of light. So as you fall into the black hole, the time on the spaceship is going slower, which means the intervals between the flashes are getting farther apart. And so from outside, I see you falling into the black hole. You have 1 second, then 2 seconds, then 3 seconds. This flash gets further and further apart, and I see you fall in until just about the event horizon. I see that I don't see another flash. I see a flash, and then I don't see another one, because the time interval between the flashes has effectively become infinite, because time has slowed for the person traveling to such a great extent that it no longer is essentially, time is not elapsing for that person from this person's perspective. So this guy on the outside, you're watching you go in. I wait. I don't see another flash. I wait a month. I wait a year. I wait 10 years. I don't see anything. I assume you're dead. I fly off. Now, from your perspective, remember, you just flew straight into the black hole, and you're checking out this black hole, and it's amazing. Well, you take a moment to look up, and you look up and you watch the entire universe elapsing, because time is not moving for you, but outside in the universe, years are flying by, centuries are flying by, millennia, billions of years are flying by. And so by just merely glancing up, you get to watch the entire universe elapsing right in front of you like a fast-forward movie. And that's because of time dilation. So we want to talk about worldlines, and worldlines are a way of drawing space-time in a way that we can visualize. So our worldline is a line in space and time. So let's do this. Let's draw a graph where we're going to have x and y like this, and I'm going to put, let's see here, I want to put space on this axis. And by space, you can just imagine, space is just your position along some path, right? So if I had a path like this, say from my house to the university, my space position would just be how far along I am on this path. So this might be 1 mile along my path. This might be 2 miles. Right? So that's the position on this horizontal axis. And then we can put time on the vertical axis. And we usually put these things in terms of space in light years, which is the amount of time or amount of distance light can travel in a year. And we put time in terms of what do we put time in? Time in terms of years. Yeah. So we have light years and we have years. And this is just a way to graphically represent our coordinates in space and time. Because remember, space and time coordinates, we've got our space coordinates, x, y, z. That's what we're calling space. And we have our time coordinate, t. And we're just drawing a little diagram like this. So let's first draw one with u at rest. Okay, so if I draw you at rest, I have my world line here, and I ask you to draw yourself at rest in the same spot, but you're still going forward in time. Now, we can't stop time from elapsing. You can try. I can't do it. Time's still elapsing. It's still going. It's still going. I can't stop it, right? So we can't stop our travel through time, but we can stop our travel through space by just staying put. And if I do that, that means that I'm just going to get a straight line going up in time. So this is the direction that I'm moving. And I go 1 hour, 2 hours, 3 hours. That's just me sitting in my chair. Okay. I haven't moved in space. I've only moved in time. Now, if you were in a car traveling at 60 miles an hour, right, we could draw that trajectory on our space-time diagram. That would look like this. After 1 hour, I would go 60 miles, so I go up an hour, and I go over 60 miles. I can go up 2 hours. That goes over 120 miles, go up 3 hours, over 180 miles, and you can see that that's a slanted line at a constant velocity like that. Now, if I'm going faster, what's going to happen? If I'm going faster, the angle gets steeper, right? So if I'm going faster, that's 120 miles, 240 miles, 360 miles. That's if I'm traveling at 120 miles an hour. I'm still elapsing in time at the same rate, but I've gone through further space. Now, if I extend this out to traveling at the speed of light, then if I go at a car at the speed of light, it looks like this. I get to the point where if I'm measuring this in years and light years, then the speed of light is at a 45-degree angle, and I cannot go faster than that, right? I can't go faster than the speed of light. You might ask, why can't I go faster than the speed of light? Well, the reason you can't go faster than the speed of light is that the closer you get to the speed of light, the more energy it takes to accelerate you closer to the speed of light. And by the time you're at 99.9999999% the speed of light, it would take more energy than is contained in the entire universe to accelerate you that little last bit to the speed of light. And so we can never reach the speed of light. We can only get arbitrarily close. So as I speed up the car, this was 60 miles an hour, this was 120. The angle gets bigger, 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 bigger until I get very, very close to the speed of light, and that's the best that I can do. And so what that means is that we have sort of these exclusion zones on our space-time diagram. These exclusion zones tell us that any event that occurs over here, I can't know about it, right? So let's imagine what I mean by an event, right? So let's say I'm sitting here, and I'm just sitting at rest, and I have a friend who's over here, and they say post to Facebook, right? So they post to Facebook, and when they post to Facebook, that's an event that's traveling at the speed of light along the distance between us and them, right? So that's, I type, I'm sitting in my chair, hit return, and that travels across the network at the speed of light. So it takes time for it to reach me. So here I am, the event travels at the speed of light, so it's at a 45-degree angle. I'm moving in time, right? And you'll notice that I hear about the Facebook post at this time, right? So I couldn't know about it until enough time had elapsed so that it was in my world line, that it crossed my world line. And so this is the part I can know about, and this is the part I can't know about. And this becomes important in astronomy because the universe out there, it's huge, and it takes time for light to reach us. So if instead of a Facebook post, I instead had a star explode, there's a supernova explosion, and light travels from the supernova explosion, right? It takes time to elapse. You know, this light wave is traveling at the speed of light. It takes time for it to get to me. And so when I see it, I'm seeing something, the light that is reaching me left this object at some distant time in the past. And so when I look out into space, I'm literally seeing the light from the past. Because light travels at a finite speed, and when the event occurred, it was outside of my my event cone, right? It was outside here, and I had to wait for time to elapse before I could see that event. And so the implication of space-time is pretty exciting. It means two things. It means that effectively it makes space travel pretty easy as long as we can travel close to the speed of light. We don't have to worry about freezing ourselves or anything like that if we can get fast enough. But more importantly, the second thing it means is that time travel is a reality, right? Time travel is a reality because if I want to travel forward in time, all I have to do is travel very, very fast. Time will slow down for me. And if I wanted to go 1,000 years into the future, I would just go at near the speed of light, 500 light years out, 500 light years back, and I could see what the world looked like in 1,000 years. You want to travel into the past? Just look at the sky, right? Go outside tonight and look out at the night sky. Find say the Andromeda galaxy with a pair of binoculars that's 2 million light years away. That light left Andromeda 2 million years ago, and you were seeing that object as it really was 2 million years ago. So you're literally seeing back into time. So that's pretty exciting. You can just go out there and do that tonight. Now this is going to become important as we go forward because we are going to be looking very, very far out into space, and we will be traveling very, very far back into time and using the principles of special and general relativity when we do that.